Okay, hello everyone. So I am here to talk to you about automatically finding bugs in ZK circuits. And so I'm going to start by giving you a little bit of a background. So when someone writes these ZK circuits, they're going to write it in a particular language. So here are two languages that we have. One of them is Circom. Another one is Halo 2. Both are fairly commonly used in order to write these circuits. And the important part is once someone implements a circuit in one of these languages, it's going to produce two things, the witness generator and the constraints. And so we have a picture of those two things, and those constraints are used by the snark in order to implement the prover and the verifier. So this is what happens, that's the main meat of the circuit, right? And so the important part here is when someone ends up implementing these circuits, they normally have this desire to make sure that the witness generation and the constraints are equivalent. And so what I mean by that is something very specific. So basically you have a witness generator which implements some program P. It takes as input like X and it's going to output Y. In addition, as I already mentioned, you're going to have a set of constraints. Let's call them C. They're going to take in the inputs of those programs and also the output of that program. And in the end, it's just going to return true or false. And so basically what you want is you want to make sure that for every input and output of P, they will be accepted by your constraints if and only if your constraints actually match. So basically, for every input-output pair that you have of P, your constraints must be satisfied. And then in addition, for every input-output pair that satisfy your constraints, you want to make sure that they belong only to that witness generator. And so that means that your circuit is deterministic. And so what we're going to be talking about here is how you might be able to violate that. And so we already talked a little bit about these two requirements. So basically for every input-output pair, P satisfies C. And for every input-output pair that satisfies C, you want to make sure that they were produced by your witness generator. And so that leads to two types of bugs. So you have over-constrained bugs where your constraints are not permissive enough. So basically, they are too constrained, and some of the inputs and outputs produced by your program are not going to be accepted by your constraints. However, in most ZK languages, when you add a constraint, it's also going to manipulate the witness so that this doesn't happen. The witness will fail in that case as well. So we're just going to skip this particular case, and we're going to focus on this other case. And so these are under-constrained bugs. So an under-constrained bug happens when there's some pair of inputs where the constraints are satisfied, but they were not produced by your witness generator. And so let's go and take a look at how that might happen. Oh, well, I guess maybe first I should say why we care. So we care because these have occurred, in the past. And so you can see here some examples of where we've seen these under-constrained circuits. So Tornado Cache, if you looked at their Medium blog, that was due to an under-constrained circuit. Veradice actually in the process of verifying the BigInt library of circumlib found some under-constrained circuits, and recently Aztec, I think, reported some under-constrained circuits. And so in this talk, we're going to talk about how we're going to avoid such bugs. And so we're going to talk about, there it is, 3 tools in particular. And so those are Orca, Vanguard, and Picus, and how they interact with each other, because they kind of have some synergies that I want to highlight here. So first, we're going to talk about Vanguard. And so basically what Vanguard is going to do is it's going to take in your source code. This could either be Circom or it could be Halo 2. And basically what Vanguard relies on is the fact that many of these ZK bugs follow some sort of a pattern. And so what I mean by that is if the pattern holds in a particular circuit, then it's likely to be buggy. And so we identified a lot of these patterns, and we put them in ZK Vanguard. And at the end, we basically let the user know what those bugs are. And so let's go ahead and take a look at an example of this. So here we have a Circom circuit. And what this Circom circuit implements is a basic bit adder. And so what that means is it's going to take as an input 2 bits. And it's also going to output and it's also going to take in a carry, which is going to be the output from the previous adder, presumably. And as an output, it's going to put the result of that arithmetic. And so, however, if we go ahead and we look at how this logic actually looks, we can see a couple of things. First, the user is going to constrain those inputs, which is great. And so that's constraining them to be bits first. And then it's also going to constrain the outputs. And so the important thing here is that if you look at the computation that's performed, and that is specifically performed in, let's see if I can get this working, these lines right here with that single arrow, they don't quite look the same as how someone is performing those constraints. And so the important thing to note here is that when someone uses this operator right here, that is only going to put that computation within your witness generator, but it's not going to add any constraints to your circuit. In addition, similarly, this is going to add constraints to your circuit, and it's not going to have a big impact on your witness generator. So let's see what happens when we feed this into Vanguard. So you can see here that Vanguard identifies, something. And so specifically, it says that there are some input signals that are not properly constrained. And so the reason why that is because, those input signals are constrained to be bits, but they're not entirely constrained. So it doesn't, they can have alternate values. In addition, we can see here that it's also reporting that there are some output signals that are not constrained. In particular, it says that the two output signals right here are not constrained. And so the important thing to note is that static analyzers can produce some false positives. So here, in this case, it's okay that those inputs are not properly constrained. However, we're not quite sure if this second case is actually true. Do we actually care that those output signals are not constrained? And so that's what we want to know. So basically, we can use Vanguard in order to give us quick feedback, in this case, point out some potential issues. And then that is something that the user can go and investigate to try to figure out whether those issues actually do exist or they don't. And so in practice, Vanguard has a relatively low false positive rate, but it can still have false positives. And so now I'm going to talk about how you can deal with those false positives in another automated tool that we have, which is Orca. So what Orca is going to do is it's going to take in your constraints, and it's going to output one of two things. So it can either say that your circuit is under-constrained, and it will provide you with concrete evidence of your under-constrained circuit, or it's just going to say, I don't know. So the reason why it's going to do this is because Orca doesn't provide any concrete guarantees about whether or not your circuit is constrained. It's just going to try to figure out if it's under-constrained and provide you with evidence of, that fact. And so the way that we do this is we use a technique called fuzzing, which basically performs random mutations in order to find evidence of concrete or evidence of exploitability. And so the way that we do this is we're going to take an input, and we're going to randomly mutate it, and see if the verifier is going to accept one of those random mutations. And so here, if we feed it that buggy implementation that we talked about earlier, where you can see that Orca is going to find something. And specifically what it says is that, there was this original witness that you gave me. In particular, it was the witness that would be generated by the program that we looked at earlier, or the witness computation that we looked at earlier, where, if you take in this series of inputs, it's going to produce, the correct output. However, what Orca notes is that because two of those signals are only constrained to be bits, but not the actual value that matches the computation, you can actually manipulate that value. And so specifically, it says carry can be 1. And so if we walk through here, that basically says what I already did. And then this is where the issue comes in. So it's going to compute the outputs from the input. But as I pointed out earlier, that's only going to happen in your witness generation and not in your constraints. And so in particular, that's because of these operators, which I pointed out earlier. And so the problem that we have here is that the user has not properly constrained or has not added proper constraints in order to make this circuit deterministic. And as a result, a user can, or a malicious user in this case, because most likely they do want to make sure those outputs are constrained, can manipulate the output of this adder so that it can return something that is completely false, something that should not happen. And so now we can go and fix the bug. And so if we fix the bug, we get a new implementation. I'm not going to walk through this just because, I'm a little bit limited on time. And so essentially, it's going to convert to bits rather than what we did previously. And it's going to use a safer operator, which is this one right here. And we're going to use another tool that Veridice has developed called Picus. And so what Picus does is it, again, takes in your polynomial field equations. And it's now, because Picus is a formal verifier, it can actually output whether or not your circuit can be proven to be constrained. And then, in addition, Picus can also produce evidence that your circuit is under-constrained. And in some cases where Picus does not quite scale, so maybe because it's a particularly large circuit, for example, it's going to say, I don't know. And so the way that Picus does this is it combines the strength of two techniques, SMT and static analysis. And so the reason why we do this is because static analysis is fast, but it's imprecise, which means that there are going to be some signals that it can't necessarily say are constrained. And SMT is very precise because it can reason about the semantics of your circuit, but it's also very slow. And so in order to improve the scalability of this verifier, we have this synergistic way of combining both of those techniques in order to prove larger circuits, or prove the correctness of larger circuits. And so this is also open source, which is why that's there, if anyone wanted to check it out. Anyway, so if we ran Picus on this fixed version of the circuit, essentially what it's going to do is this. It's going to take a look at it, and it will do some pre-processing, and then finally it will report that this circuit is now safe. And so that means that now the user knows that their fixed version of the tool is actually fixed, because they might not have fixed it correctly. And so in the case where Picus reports safe, it's guaranteed not to have any under-constrained signals. And so each of these tools have complementary strengths. So Vanguard identifies potential bugs. Orca can give you concrete evidence that those bugs actually exist. And finally, Picus can prove that your implementation is correct. And so, in conclusion, I talked to you about three bugs that we're developing to find, or three tools that we're developing to find bugs in ZK circuits. And in addition, we're an auditing company and have worked with a number of players in the ZK area. So if you're interested in talking to us about any of our audits, or you want audited, let's talk. Anyway, thank you.